Hello friends, in the previous video we will discuss about the phases of compiler. So in that video analysis part phase is over. So that means the first three phases of compilers are completed. So the first three phases of compilers are lexical analyzer, syntax analyzer and semantic analyzer. So up to this I'll stop it in the last video. So the output of the lexical analyzer is token, and the output of the syntax analyzer is a parse tree. Output of the semantic analyzer is annotated parse tree or corrected parse tree. So up to that, I'll stop in that video. In this session, I'll continue with the intermediate code generation and the remaining two phases. So in this intermediate code generation, this is the fourth phase of the compiler and it is common for analysis phase as well as the synthesis phase. Here the source program, it is a intermediate code generation. We can follow the three methods. For generating the intermediate code, we can follow this three method: postfix notation, tree address code and syntax tree. But here we are going to discuss only about the three address code. There is one more topic in the one more unit, intermediate code generation. It is a separate topic, separate unit. So in that we will discuss about what is meant by postfix notation, how we can generate the intermediate code using postfix notation as well as the syntax tree. So today in these phases of compiler, we will see only about the three address code. For that, first we have to know about what is meant by three address code. In this three address code, we have to follow two rules. First one is the left hand side of that expression, it contains only one operand. It must. And right hand side, it should be only one operator. The operands may be one or two. Maximum one operator, or otherwise there is no operator. That is also not a problem. So these two are the important rules we have to follow for three address code. This is the key term again used in intermediate code generation. So I'll explain it in the example. Here this is the output for the previous phase, that is the semantic analyzer phase. So in the semantic analyzer phase, we are checking the type, data type of each and every variable. So here the id1 is nothing but C, id2 is nothing but A, id3 is nothing but B. These three variables are declared as float, but only 5 is as integer. So in the previous phase, we can convert this integer data type into float with the help of this type conversion into float. So it is used to convert integer to float. Now the value here, it is nothing but 5.0. So this is the output for the previous phase, that is semantic analyzer phase. Now we can use these as input to the intermediate code generation, and we are generating the intermediate code, that is nothing but the three address code here. How we can generate the three address code, I'll explain it here. uh, for three address code, definitely we need some temporary variables. Here the temporary variable, first temporary variable is t1. So t1 equals into float of 5. That means we can convert the integer into float. So it is nothing but into float of 5. Otherwise, it is nothing but 5.0. Instead of 5.0, here we mention like this, into float of 5. This part is over. Next part is id3 into float of 5. So for that we need one more temporary variable t2. T2 equal left side is id3 and the operator here it is asterisk, and right side is into float of 5. That is already we assigned to t1 variable, that is the t1 temporary variable, so we can mention it as t1 here. Up to this it is over now. Now id2, for this we need one more temporary variable t3. T3 equals id2 plus this thing id3 asterisk into float of 5. This is stored, this value is stored in t2. So ID2 plus T2 here. Now the right hand side is over. We can assign this value to ID1 now. So ID1 equals T3. Finally, the value is stored in T3. So now we can assign that T3 value to ID1. So this is nothing but the intermediate code generator. In this intermediate code generator, the same thing is written here. So in this intermediate code generation, as I already told, you can check left side there is only one operand T1, T2, T3. It may be temporary variable or whatever the variable we declared in the source program. So this is the left side there is only one operand is there. And right side you can check maximum only one operator. For T2 and T3 there is only one operator asterisk and plus. And the operands are two operands. For T1 and ID2 only one operand is here. For ID1, the temporary variable T3 is used and T1, the number is used here. So there is no operator, that's not a problem. More than one operator is there means it is not a three address code. The main thing is right hand side there is only one operator is must. So these are some properties of intermediate code. It should be easy to produce. And here we can it is in the middle of the phases of compiler, so from here onwards it is easy to translate into the target program. So that is the main properties of the intermediate code. Next phase is code optimization. So for code optimization, the input is the three address code that is already generated in the previous phase, intermediate code generation. So now this is input and output is the code optimizer. So before that we have to know about what is meant by code optimization. So here we can optimize the intermediate code. What is meant by optimization? We can run the code in faster way. Suppose if there is any redundancy in your code, we can remove that redundancy, or we can reduce the number of lines in the code of the program, but it should not affect the result. So that is one more important point, and there are some more points are there. So during code optimization, the same thing, reduce the number of lines in the code. So redundant code is there, you can remove the redundant code, then it is faster, the machine will be run faster. But if you are removing the duplicate code or reducing the number of lines, the result of the program is not affected. That is the important point. It should not affect your result. The original code should be the same. So how we can improve the code optimization or code generation means detection and removal of dead code. Dead code means unreachable code. That line is never used in your program. It is not a reachable one. And the next one is a calculation of constants in expression and terms. Suppose if you are using any constant term instead of expression, for example here t1 equals into float of 5, it is like a operand. So instead of this directly we can use the number. I'll explain it in the example. So instead of that line we can remove that expression. Directly we can use the constant value. That is the best way to improve the machine code. That is running the machine code will be improved if you are removing the expression in terms of constant. Similarly, there are some more points. Collapsing of repeated expression, that is a redundancy expression. Loop unrolling, that loop is never used in your code. Removal of unwanted temporary variables. So these are all moving code outside the loop. That means outside the loop, once the loop is executed, some codes are available outside the loop. There is no use of that code. So that type of code will be removed. So these are all the some steps to improve the code optimization. So here this is the output of the previous phase. 4 lines are available here. But after code optimization, we can reduce that 4 lines into 2 lines. So how you can reduce? Here t1 equals instead of into float of 5, we can use it as 5.0, correct? So into float of 5 is nothing but it is 5.0. So T1 equaled ID3, this second line. We can rewrite the second line here. The temporary variable may be anything. Don't confuse here T2 is there, here T1 is there. That's not a problem. We can use any temporary variable. Here we can use the new temporary variable T1 equals ID3. ID3 is there, asterisk. T1 is nothing but into float of 5. So instead of into float of 5, directly we can write 5.0. That means it is a float number. So no need of the first line here. So you can remove this. So this is nothing but the constant in expression. Instead of using some command, directly we can use that value here. So this line is removed now. So in the next line, id1 equals id2. So here we are assigning t3 to id1. Instead of this line, directly id1 equal to id2 plus whatever the information stored in t1. So now you can check id1 equal to id2 plus t1 is id3 into 5. It is similar to your original code. There is no change in the code. So that means here the result is definitely not affected. But the code optimization, that the number of lines is reduced here. In the previous phase, there are 4 lines of code, but here after code optimization, we can remove the first line as well as the last line. We can reduce it into 2 lines. So it should be faster compared to the previous one. It is nothing but it is the optimized code. Now this is the output for the optimization phase. The last phase is the code generation. So in this code generation, we are generating the assembly language code or the target code. This is the final phase of the compiler. So here, after converting that optimized code into machine code or target code or assembly language, now it is ready to execute. We can get the object code as a result here. So for that code generation, we need some register and memory. So how we can load all the information? So generation of correct reference and generation of correct data types and generation of missing code. So we can concentrate on all this. I will explain this it in the example. So this is the output for the previous phase, that is the optimized code or code optimization phase output. Now we can give this as input to the code generator. So here for identifier, we need some register. So for that, first one is you can use any register. Instead of R2, we can use it as R1. That's not a problem. So first ID3 is a identifier. We can move that identifier value to one register. Here name it as R2. It may be R1. That's not a problem. So load, LD is nothing but load. Here F is nothing but all the variables are declared as float data type. So for float data type, we are using the F here. If it is integer means no need of F. Just we can mention it as LD. So LD F R2 comma ID3. That means the ID3 value is moved to the register R2 or it may be R1. So that's our wish. So this part is over. Now this identifier is moved to one register. Next one is multiplication operation. Mul F. Mul means nothing but multiplication. Again F is for floating data type. We are multiplying ID3 with the value 5. Here instead of 5, we can mention it as 5.0. By mistake here 5 is there. It is not 5. It is 5.0. So if it is a constant value, we can mention it in before that constant value or constant number, we can use hash symbol. Okay, that means it is a constant value. Multiplication, it performing the multiplying operation R2 contains ID3. So here R2 is nothing but ID3. That ID3 is multiplied with the constant value 5. So finally again the result is stored in R2. Here the R2 value is different. Now here the R2 value is different because in this R2 only we can move the value of ID3. Here after performing the multiplying operation with ID3 and 5, that result is stored in this R2. So this line is over. So this is the assembly level language or target code for the first line. Similarly, do the same thing for second line. So here there is one more identifier ID2. So for that we need one more register. Here R1. Suppose here if you are using R1 means here it is R2. So move that identifier ID2 to R1 LDF. Load ID2 value to the register R1. The data type is F. So LDF R1 comma ID2. Now this value is moved. Here the operations were performed is plus. Again here there is a mistake. It is not asterisk, it is plus. So for plus it is a addition operation. Add, which values are added here? ID2 and T1. T1 value is already stored in R2. So now we can ID2 is in R1. So we can add R1 and R2. Clear? So here if there is a, here we are performing addition operation ID2 plus T1. That's the reason here add function is used. Again the data type is float. Which two values are added? ID2 plus T1. ID2 is in R1. So R1 is here and T1 value. T1 is ID3 into 5. That is stored in R2. So R2 is here. Now performing the addition operation between R1 and R2. That result is moved to R1 here. Finally, we can store the value in that identifier ID1. So the final result is stored in R1. Now we can store that value in ID1. So this is the assembly level language code. There is a difference between identifier to register as well as register to identifier. If that is memory, register to memory, if you are moving a value from memory to register means just we are storing the value. Yeah, vice versa, suppose if you are moving a value from register to memory means it is ready for execution, that value is ready for execution. So this is the final assembly level language code for this input. So this is the final phase. This is the common diagram for all the phases. First phase. For first phase, the input is the source program. The tokens are generated. After lexical analyzer, this is the input source program, high level language. So you can give this input to the lexical analyzer. The output is the token. It is represented within the angle bracket. There is a template. Now that token is input to the syntax analyzer. Here the parse tree is generated. So now this is input to the semantic analyzer. Here we are checking the type checking. So the remaining variables is C, A, B are declared as float. Only 5 is integer. So we can do the type conversion here, integer to float. Now the 5 is changed to float. This is input to the intermediate code generation. So in intermediate code generation, the 3 address code is generated here. Intermediate code is generated here. Now this is input to the code optimization. In code optimization, the number of codes are reduced or the redundancy codes are removed or dead codes are removed. So there are many points. Only thing, the result will not be affected. That is the main thing. Here the 4 line is reduced to 2 lines, so the compiler compiles the code faster way. Finally, in the code generation, we can convert this optimized code into the assembly level language code or target code. So this is the assembly level language code. These are the 6 phases of the compiler. The first 3 phases are comes under analysis pass, and the last 2 phases are comes under synthesis pass. Intermediate code generator is common for both analysis and synthesis pass. That's it. These are the 6 types of say or 6 phases of compiler. Thank you.